Hello everyone and welcome to the short presentation on hardware-based fast real-time image classification with stochastic computing. The goal: to use stochastic computing to realize medium complexity convolution neural networks targeting real-time applications. Nowadays, various IoT devices generate huge amount of data at the source and are dependent on edge and cloud computing to process their data. Stochastic computing can be used for near sensor computing, where data can be processed locally. It can also overcome the dependency on edge and cloud computing for medium-sized real-time applications. Also, the associated problems like privacy and security, latency and speed can be overcome and thereby improving the overall performance of the application. Stochastic computing. It's a non-conventional low-cost approach where numbers are treated as digitized probabilities. Such numbers are called as stochastic numbers. For example, the binary number 0.75 can be represented as shown here. Both the representations has 75% ones and 25% zeros. The bit stream length is 8 bits wide. Circuits that process such numbers are called as stochastic circuits, and they have advantages like low complexity, power efficient, inherent error tolerance. For example, a single bit flip from 1 to 0 in the above number 0.75 would be a number 0.625, which is still the representable closest of 0.75. Also to note here, the position of ones within the bit stream is independent of the bit position because each bit position has the same weight. Here are the example of stochastic circuits. For example, AND gate is used as a stochastic multiplier to multiply two stochastic numbers. And also we have the two input mux, which is acting as a scale stochastic adder. The choice of convolution neural network is the popular LNet-5 neural network. The architecture is shown here. It has two convolution layers with 6 feature extractors in the first layer and 16 feature extractors in the second layer. In addition, it also has 3 fully connected layers with 120 neurons in layer 1, 84 neurons in layer 2, 10 neurons in layer 3, which is also the output layer, which represents the possible 10 class outputs. In addition, each of the convolution layer is also followed by a max pooling operation. The input layer holds the input images, which are handwritten numbers from the MNIST dataset. The images are passed through convolution layer, followed by max pooling, and then the second convolution layer, and followed by another max pooling. The output of the second max pooling is flattened and is then fed to the fully connected layer. The number of trainable parameters and the number of connections that exist in each layer is shown at the top. The neural network is first built using C++ and is then trained using the MNIST training dataset and is then tested against the MNIST test dataset. The trained parameters are then extracted and is used to realize or construct the stochastic version of the convolution neural network. Stochastic convolution neural network building blocks. These building blocks are the components that are used to construct each layer within the stochastic convolution neural network. They are listed in the order of data propagation within each layer. Stochastic number generator. This is the source of stochastic numbers within the stochastic convolution neural network. All the trained parameters and the input pixel, which are in binary, are converted to their equivalent stochastic numbers. It is constructed using a random number source, which is a linear feedback shift register, and a 4-bit lookup table, which is also called as SPOCs. The advantages of using this number generator over the other available ones is that it has reduced correlation between multiple stochastic numbers generated from the same random number source. The next component is the stochastic computing neuron. The schematic is shown here. It consists of a set of AND stochastic multipliers to obtain the products between the input pixel and trained weights. Then we have the router logic that is used to route the negative products to the negative parallel adder and positive products to the positive parallel adder. The binary sum out of the parallel adders is fed as an input to the FSM-based stochastic sigmoid activation function. Here is a plot of binary versus stochastic sigmoid activation function. The blue line represents the binary version while the orange represents the stochastic version. The output of stochastic neurons is fed as inputs to the stochastic max pooling unit. It accepts 4 stochastic numbers from 4 stochastic computing neurons. This is because the size of max pooling window is 2x2. The advantage of using this max pooling unit over the others is that it can output the exact maximum of the 4 input stochastic numbers. The choice of stochastic number precision is 9 bits. This means All the train weights and the input pixels are all represented as 512 bits. Realization of Stochastic Convolution Neural Network. The choice of FPGA is the Xilinx XC7Z020. It offers a heterogeneous computing platform consisting of programming logic fabric and processing system, which is ARM Cortex-A9 CPU. The complete stochastic convolution neural network is realized on the programming logic fabric, which is shown in the red box here. It consists of an input layer, which is used to hold the input test images from the MNIST dataset. It also orders the correct pixels required for convolutional operation and also generate their equivalent stochastic numbers. Next, we have the first convolution layer, second convolution layer, and the three fully connected layers. Each of these layers mainly perform stochastic number generation, convolution, accumulation, activation function, and subsampling. The last layer performs classification operation. Each of these layers has got their own stochastic number generators. These generators are used to generate the stochastic numbers for the train parameters and the input pixel. Also, each of these layers has got their own instances of stochastic computing neurons, which perform multiplication, routing, parallel addition, activation function, and max pooling operation. The processing system, or the ARM Cortex-A9 CPU, executes a bare metal application. This bare metal application has got three main tasks. Initializes UART, GPIO, SD card interface. It then loads all the train binary parameters, the 10K test images from the MNIST dataset and their labels from the SD card onto onboard DDR3 memory. At last, it performs evaluation of SCNN results against the test labels and then reports the classification summary via UART. Design decisions. The stochastic convolution neural network is designed for resource-restricted FPGA with resources as shown. Certain components within each layer is designed to be modular in nature and are subject to time multiplexed operation within the layer to complete the operations of that layer. For example, there exists only one hardware instance of SC neuron in the first fully connected layer and is used 120 times to finish the operation of that layer. Storage of intermediate stochastic results between the layers is achieved by using block RAMs and the associated control logic around it. Results. Classification accuracy. Now we have two models of the same Len5 neural network. One is the stochastic version and the other is the software version. Both of these models were subject to 10,000 MNIST and FASHION MNIST test images. It is evident from the results that the stochastic convolution neural network almost performs identical to the software version in terms of classification accuracy. Results. Power estimation. The FPGA development board has got only one current sense jumper pin to measure the overall power consumption of the board. There is no facility to make individual power measurements for each of the components present on the board. Hence, a separate power measurement for the FPGA alone was not possible. However, a sequence of power measurements was made during the operation of the board to get a more realistic power estimation of the stochastic convolution neural network. Power measurement was made when the board was powered on, programming logic configured with stochastic convolution neural network, and the processing system is running. Stochastic convolution is running and doing the classification task. Stochastic convolution neural network finished the operation. From the table, it is clear that the power estimation when the stochastic convolution neural network is running and not running is approximately 96 milliwatts. Conclusions. A fully working and self-contained stochastic convolution neural network is developed, which can do real-time classification of handwritten numbers. The complete stochastic convolution neural network is realized just by using 52% of the available lookup tables and 25% of the available flip-flops in the FPGA. From the results, it is evident that stochastic computation can do accurate real-time image classification with small, low complexity and low power circuits. The previously explained stochastic convolution neural network building blocks can be arranged in a large variety of different configurations and thereby enabling many areas pre-designed trade-offs. References. Thank you for listening.